All classical approximate solution methods can be divided into two groups: weighted residual method and variational method. The basic step in both classes of method is to assume a general form of the trial solution, usually a polynomial based trial solution. Using weighted residual method, we operate directly on the governing differential equation, whereas in the variational method, the governing differential equation is first casted into its equivalent variational form, and then we incorporate some trial solution into the resultant equation. What are the different steps in the weighted residual method? So weighted residual method operates directly on the given differential equation. So let's consider a very generic form of the differential equation, L2m phi equals to f, in which L2m is a linear differential operator of order 2m. Phi is a state variable which needs to be calculated, and f is a forcing function. So this is a very generic form of a differential equation. For example, in the case of axial bar problem, we had the differential equation EA d2u over dx square equals to minus q, in which the linear differential operator is d2 divided by dx square. Sorry for this EA term. So this is a constant. This is not a linear differential operator. So L2m is d2 divided by dx square. The state variable phi is u, and the forcing function f is minus q. Okay? So this is a very generic representation of the differential equation. So now for the given differential equation, the exact solution is not known to us. Therefore, we seek for an approximate solution of this differential equation. And the basic step is to assume a trial solution satisfying the boundary conditions. Usually, we assume a polynomial solution with some unknown coefficient. For example, you can assume a trial solution, and you'll think that this solution might be the solution of this differential equation. And let's say you have assumed a polynomial trial solution a0 plus a1x square plus a2x cube plus something. Now the problem is to find the unknown coefficients such that phi trial, the trial solution, is exactly equals to the exact solution. So you will put the trial solution in this equation, and it must be equals to f, or L2m of phi trial minus f must be equal to 0 if phi trial is the exact solution. Right? So if we substitute phi trial in the governing differential equation of the problem, we can expect that there would be some residual, because phi trial is a trial solution. It might be an exact solution and it might not be. And if it's an exact solution, so this must be equal to 0, but usually it is not. So it means that we will get some kind of residual. Now our key task is that for phi trial to be exact solution, this residual must be equal to 0, or approximately approaches to 0. At least it should approach to 0. It is possible that this residual may vanish for some values of x. At some particular location, the residual of this differential equation might be equal to 0, and this phi trial solution might be representing the exact solution at some particular points in the body, but not for all values of x. A good approximation to the exact solution would imply that R is small at all points of solution domain. So it means that in an average sense, that the sum of all r's must be equal to 0, or the integral of r must approach to 0. Most commonly, the different methods under the category of weighted residual methods, they are symbolized with this particular equation, in which instead of writing down the integral of r must approach to 0, usually we can symbolize different weighted residual methods as that the integral of some weighting function multiplied by r must be equals to 0. So this is the key equation for the weighted residual methods, that we want the residuals must be close to 0. And then the problem is to determine the unknown coefficients AI so as to make the weighted average vanish over the whole domain. So over the whole domain, in an average sense, the residual must vanish, or it must approach to 0. So let's consider a differential equation. So it's a second order differential equation, minus d2u over dx square equals to sine pi x. The domain of the body is expressed x greater than 0 and x is less than 1, and with the following boundary condition, that u at x equal to 0 is 0 and u at x equal to 1 is also 0. Luckily for this differential equation, the exact solution is known to us, which is given by this particular solution. But let's say we don't know the exact solution and we would like to use some approximate solution methods to find out the solution of this differential equation, that is the equation for u. Now, according to the weighted residual method, or in the approximate solution method, first of all, assume the trial solution in the form of polynomial a0 plus a1x plus a2x square, and when you will put this solution back in this differential equation, the residual must be equal to 0, but that residual might not be equal to 0. There will be some difference between the approximate and the exact solution, and let that be denoted by residual r. This residual is then multiplied by some weighting function and integrated over the whole domain. So we would like to, the problem is then to find out the unknown coefficients a0, a1, a2 and so on, such that the residual minimizes or the residual approaches to 0 or to some minimum tolerance limit. And then based on the definition of the weighting function, different methods are there. So different methods of weighted residual differs in the way the weighted function is defined. So least square method, collocation method, Galerkin method, modified Galerkin method, each of these methods were developed independently, but later on it was realized that each of these methods can be symbolized under one method. So they realized that in each of these methods the residual is multiplied with some quantity, with some function. So they generically called it a weight function, and if the residual is not multiplied with anything, even then they assumed that the residual is multiplied with 1 or unity. So the weighting function is 1 or unity. So these methods were developed independently, but later on it was realized that all of these methods can be symbolized under one category, and their generic form of residual can be written down in this function, where a weight function times residual over the whole domain must vanish. So let's try to discuss first method of weighted residual method, the least square weighted residual method. So again, the first step in the solution of the least square method is to assume the polynomial trial function. So in this case, let's say I am assuming a quadratic trial function for this particular problem. So I want to determine the approximate solution of this differential equation, and I am assuming a trial solution, and let's say I have assumed a quadratic trial function a0 plus a1x plus a2x square. This trial function must satisfy the boundary condition, that is at x equal to 0 u must be equal to 0. Put x equal to 0 in this equation and u of x 0. So I will get a0 is equal to 0. The other boundary condition is at x equal to 1 u is equal to 0. So put x equal to 1 in this equation and u of x equal to 1. I will get a1 is equals to minus a2. Putting the values of a0 and a1 in the above equation, I will get the admissible trial solution. So this was the generic trial solution, and this is the admissible trial solution which respects the boundary condition, which is satisfying the boundary conditions. U of x equal to this. Then this equation requires me to calculate the second derivative of u. So now I calculated the first derivative of u, this function, and then the second derivative of u, and then now I'm incorporating this second derivative into the differential equation. Minus d2u over dx square minus sine pi x must be equals to, if it's an exact solution, it must be equal to 0, but it's not, so it must be equal to residual. So this is the equation of the residual. Now this above equation is required to be solved for the unknown coefficient a2, right, for this coefficient a2. In the least square weighted residual method, weight function is the residual itself. So this is the equation of the weighted residual, weight function multiplied by residual, but in the least square method the weight function is the residual function in itself. And one of the idea was why you are multiplying a residual with a residual, to cancel out the effect of negative residuals. So there is a possibility that at some points in the member the error or residual is positive, and at some point the error is or residual is negative. So if you calculate the sum of all the residuals, so positive may cancel out the negative residuals, so you will get the net residual is 0, which is incorrect, because yes, definitely there is some residual and there is some negative residual, but the residuals are not 0. But in the summation the residual vanished. So in order to cancel out this effect, they multiplied the residual with itself, so that in order to get the absolute value. So this was the basic idea of using residual as the weighting function in this case. So now if you put weight function as equals to residual, you will get r square. The domain of the body is from 0 to 1. Now the problem is to find out the unknown coefficient a2 such that the residual rw becomes 0 or becomes minimum. And how to find out the maxima and minima? You have to differentiate it with respect to the unknown coefficients, and if I differentiate this equation, I will get this particular equation, and if I further simplify it, I'll get that this is the equation that I have to solve. So above equation is the least square weighted residual criteria. So this is the simplified form of the weighted residual equation for the least square method. So now I can also say that it's in another representation. If I would like to represent this in the form of that generic equation in this particular form, so I can say that in the least square method the residual is multiplied with this partial differential. Okay. So there is no, as I've said it earlier, that these methods were developed independently and then they were compared with that generic equation. So of course the concept of the weighting function really differs. So in the case of least square method, the weight function is represented with this differential. Let's calculate the weight function, that is partial r over partial a. Or in the initial notation, wi is equals to partial r over partial ai. Since there is only one coefficient which is unknown a2, so there will be only one weighting function w2. So this is the equation of the residual, and if I find out the differential, so I will get the weight function is equals to -2. Then I can simply incorporate in this particular equation. So -2 multiplied by the residual and integrate it over the whole domain, and then find out, equate it to 0 and find out the value of a2. So a2 comes out to be -1 over pi. Putting it back into the admissible trial solution, which was, this was our admissible trial solution. Put the value of a2 in this equation. So that is the approximate solution of our differential equation. Now let's plot it against the exact solution. So exact solution is represented with the solid blue line, and the dotted line represents the approximate solution. So I can see that it is representing the behavior somehow, but there is of course some error. It is not completely or truly representing the behavior, or it is not the true exact solution. Similarly, if I compare the first derivative of our solution function, so again I can see that it is not truly representing the material behavior. Similarly, you can, in order to improve your solution, you can use a higher order polynomial. So in this case, first of all, we assumed a second order polynomial equation. Then you can assume a fourth order polynomial, or a sixth order, or a fifth order polynomial, and you can repeat the same process, find out the residual, find out the weighting function, multiply it with the residual, integrate it, find out the unknown coefficients. So if you use the fourth order polynomial equation, so this is the red line, red dotted line shows you the solution obtained from the fourth order trial solution. Now you can see that it is much close to the exact solution. Similarly, the first derivative of the solution is also very much close to the exact solution. So increasing the order of polynomial, you are getting more close solution to the exact solution. Or in other words, I can also say that I am also increasing the number of unknowns. Of course, the accuracy is increasing, but the number of unknowns is also increasing. So accuracy is achieved with increased computational cost, right? Because I have to now perform more intense calculation, and I have to find out more unknowns in order to get the exact solution, or solution which is close to the exact solution. So this was least square method. Let's discuss the collocation method. In the collocation method, the residual is forced to be 0 at some arbitrarily chosen points. That is, I would say that r at xi is equals to 0. At some chosen points, we say that the residual must be 0, or in an average sense, at all those points, it must be approaches to 0 or close to 0. This particular equation can be written down in this form. If I would like to represent it in the form of weighted residual formulation, so I can multiply the residual with a Dirac delta function. The Dirac delta function has the property that its value is 0 if x is not equal to xi, and if x is equals to xi, its value is infinity, and the integral of the Dirac delta function is equal to 1. So it is exactly, this equation is exactly similar to this equation, but now we would like to represent it in the form of weighted residual, so that's why we represent it in an alternative form. So now for the collocation method, the weight function is actually the Dirac delta function, you can say that. Okay? Yeah, okay. Comparing it, okay, so this is what I said it. The weight function for the collocation method is the Dirac delta function. Let's try to solve the same differential equation using the collocation method. Let's again, the first step is to assume a trial solution. Let's say again I assumed a quadratic trial solution. U is equals to a naught plus a1x plus a2x square. Then that trial solution must respect the boundary conditions, so it must satisfy those boundary conditions. Based on that, I calculated the admissible trial solution. Once the admissible trial solution is there, then I incorporated that admissible trial solution into the differential equation, and I got this residual equation. Okay. Now in the collocation method, I want that the residual must be 0 at some specified points, and those specified points are arbitrary points. It can be chosen arbitrarily. So there are 100 students, so 100 students can have 100 different points which they can choose at which the residual is 0. since there is one unknown in this residual equation, so I will select only one point at which I want that residual must be equal to 0. Let's say I say that at the domain of the element was from 0 to 1. So let's say I say that at x equal to 0.5 I want the residual to be equals to 0. So put at x equal to 0.5 r equal to 0 in this particular equation and solve it for a2. So I will get a2 is equals to minus 1 over 2. So this is our trial solution. Again, if I plot it, so I will get some differences between our approximate solution and the exact solution, not only in the solution but also in its first derivative. You can improve the solution accuracy by using a higher order polynomial function as a trial solution, and then using the collocation method enforce residual to be equal to 0 at some chosen points, and then recalculate the unknowns. If you do this, you will find out that the solution obtained by the collocation method is not unique. For example, in the same problem, instead of putting residual at x equal to 0.5 equal to 0, if I say that let's enforce residual equal to 0 at x equal to 0.25 or x equal to 0.3 or x equal to 0.75, I will get completely 3-4 different answers. By changing the point at which I am enforcing the residual equal to 0, I will get completely different answers. So the solution obtained by the collocation method is not unique. Even using the same trial function, you can have different solutions. And if we take a different collocation point for the same trial function, the solution will be different. Whereas for the least square method, after selecting a particular trial solution, the solution remain unaffected. Thank you.